Hello, and thank you for coming to my talk. Today I will talk about Postgres and OpenAI, and how we can use them together on Azure to do AI on the Postgres database on the data side. A little bit introduction about me. My name is Giorgi Dalakishvili. I'm a 2 times Microsoft MVP with about 18 years experience in C# and .NET, and also on the database side, I have experience with various databases, including Postgres and SQL Server. I maintain a couple of open source projects related to Entity Framework Core. So if you are using it, I suggest you check out my GitHub profile. I think you will find them interesting. So let's start the talk. Today I will talk about AI mostly, and the demos will be with Postgres. I will talk about semantic search, about document summarization, sentiment analysis, and PII detection. So let's. So in the past, the databases used to store the data. We would query the data from the databases, and it was mostly the way we did AI. We pulled data from the databases, sent it to some server, did the analysis there, and then stored the results back in the database. This worked, but it came with a cost. We introduced latency. We introduced glue code just for pulling the data from database to the application server and doing the AI there, and then moving the results back to the database. So AI used to live outside of the database, and the sole job of the database was to store data and allow us to query the data. Today, AI services are fast. They have APIs. They are stateless, so we can directly call the various AI services from the database. This way, we can move the AI to the database side, and this lets us simplify our setup quite a lot. First of all, we can get rid of the glue code. We can get rid of the services whose all job was to get the data from the database and do some API calls and store the results back in the database. We can do this all on the database side. And the second advantage of this approach is that by doing AI inside the database, we get the results very quickly. We don't need to write the code. We can just do some SQL queries, SQL functions or procedures, and we can see the results very quickly in the editor without writing any complicated code for doing the AI analysis. And also, this simplifies managing who has access because we can already manage it on the database side. We don't need to re-implement it on the application side. So we can just control all the data access on the database side, so we don't have to reinvent the wheel. So with the Postgres database on Azure, we have the Azure AI extension, which allows us to call OpenAI services directly from the database. So we have Azure OpenAI, we have Postgres, and we also have Azure AI services. And we can this Azure AI extension works as a gateway from the database to these Azure services. So Azure OpenAI gives us access to models and vector embeddings. Azure AI services, or Azure Language Services, which is the new name, it gives us sentiment analysis, it gives us document summarization, PII detection, and also many other services that you can look up on the Azure documentation. These are just a couple of examples. So the high-level architecture, as you can see, is the PostgreSQL on Microsoft Azure, plus the Azure AI extension. The data lives there, and Azure OpenAI has models and vector embeddings, and Azure AI services has various services for doing data analysis, and we can call all these services directly from the Postgres database. So the important thing to remember is that the AI does not run on the database side. So database only contains the data, but it allows us to make calls to different services. So we orchestrate the process from the database side, but we don't run the actual models in the PostgreSQL database. The models run in different services like Azure Language Service or Azure OpenAI service. We can do summarization, we can do sentiment analysis with Azure Language Service, and with OpenAI we get access to vector embeddings and other models. So the first example that we will see is semantic search. So semantic search is different from lexical search. So the traditional way of doing search is lexical search, where we write some SQL queries with contains or like or even full text search, and it will match only those results that contain the exact word. But with semantic search, we find results that match the keyword based on the meaning of the word. So the examples may contain some different words, but the main idea is that it will match by the meaning of the keyword or the phrase that we are looking for. For example, if the user enters learning how to use a database, one of the results might be SQL crash course, because it matches on the meaning, even though it does not contain any of the words from the search phrase. The benefits of semantic search is that it can distinguish between meaning. For example, chocolate milk and milk chocolate are two different things, but with the usual keyword search, you would not be able to filter them based on the meaning. So the semantic search is able to capture the semantic meaning of the phrase that we are searching for and deliver the matching results. And also, it's easier for the users when they may not remember the exact terms that you use on your website or in your database. So they know what they are looking for. They can explain it in their own terms, and semantic search will return matching results even if you call those items or records in different terms or different words. So how does semantic search work? It works based on, so there are three main major components for semantic search. The first one is LLMs, or large language models. So large language models are trained on a huge amount of data, and they can understand the context and relationships between words. And they are the foundation of capturing the semantics of the language. With the help of LLMs, we can generate embeddings from any data, like text, images, or even audio and video. Vector embeddings are numeric representation of data, and the important feature of vector embeddings is that they capture the meaning of the data from which they were generated. This means that we can translate the data into an array of numbers, and this array of numbers captures the semantic meaning of the text or picture from which they were generated. And the third component is similarity metrics. They measure the similarity between two vectors. So if we have, so we can use them to determine whether two different terms are near to each other based on the meaning, because when we have two vector embeddings, we can calculate the similarity between them or distance, and based on this, judge how close or how far apart these two vectors are from each other. So we can, if we assume, for example, if we have a three-dimensional vector embedding, we can see that in one section we have fruits, and in this section we have different fruits. They are near to each other because all of them are fruits. In another section we will have animals. Animals will be far apart from fruits because they are not related to each other, but different animals will also be next to each other because all the animals are similar by meaning. So vector embeddings are just numerical arrays that represent the data from which they were generated. Another way to think about them is like a supermarket where we have different sections. We expect to find apples and bananas in the same part of the supermarket, but if we are looking for a magazine or something else, we don't look them next to the fruits because they are in different part of the magazine because they are different from the fruits. The next component, as I said, is similarity matrix. Similarity matrix is basically a function that takes two vector embeddings and it gives us distance between these two vectors. If the distance is low, it means that these two vector embeddings are close to each other. So the data from which these vector embeddings were generated means that these two data is also semantically similar to each other. So if we take two different fruits, generate vector embeddings from them, and calculate the distance between these two vectors, we will see that the distance will be closer. And if we take two unrelated terms and generate vector embeddings and measure the distance between them, we will have distance which is more compared to the two fruits because these two items are not related to each other. So how does semantic search work? The way we make it work is that we generate vector embeddings for all the data that we have in the database. We store these vector embeddings somewhere. In this demo, we will store them in Postgres database next to the data from which they were generated. And then when the user wants to search for something, we take the search query, generate the vector embedding again, and run the vector search on the database to find the rows that are closest to this to the generated vector embedding from the query term. So once we find those search results, we can then return them back to the user, and these will be the items that are close to the query that the user entered. So we have data in the database. We have vector embeddings generated from this data, and when the user searches for something, we generate vector embedding only for that query term and compare it to the vector embeddings that we have in the database. This way we can find the records that are close to the query based on the distance between vector embeddings in the database and the vector embedding generated from the query. So in Postgres, we have a Postgres extension called pgvector, which allows us to store vector embeddings in the database. It gives us a dedicated database type, and we can use this data type to store vector embeddings in Postgres. It also gives us functions for calculating distance between two vector embeddings. It supports different similarity metrics like cosine similarity and Euclidean distance. So we can use this extension to store the vector embeddings and also calculate the distance between two vectors. So it gives us anything that we need to implement the semantic search. It also supports different indexing strategies for vector embeddings. And because all this lives in Postgres, we get all the features that Postgres gives us. And the extension is also open source. So what are the advantages of storing the vector embeddings in database instead of using a specialized database different from Postgres? The biggest advantage is that we can store it directly in the same place where we store the data, so we don't have to set up another database. It's faster to query it with the faster and easier to query together with the data. We get operational advantages, like it's included in the backups. So we also get ACID compliance, and it simplifies our architecture and infrastructure because we don't have to care for another part of another server or another third-party service that we rely on. Basically, we store vector embeddings in the same place as where our data lives. So to use the pgvector extension, we have to enable it with this command, and then we can use the vector type like we would use any other type in the database. So we have the vector type. In this case, it's a three-dimensional vector. So we can insert vector data and then query based on the distance. So this spaceship operator that you see, it will calculate cosine similarity between the vector that is in the order by and between the data that is in the database, and give us the 5 nearest items from the database. So for querying the vector embeddings and for doing the finding the nearest neighbors, if we do it exact search, then it will get a lot slower when we have lots of data, because Postgres will have to compare our query term, our query vector embedding, to every row in the database. This is called KNN because it will return k nearest neighbors. But as the number of records grows in the database, the KNN search gets slower and slower, because it's very expensive to calculate all the distances between the data and between the vector embeddings that is the target. So the solution to this problem is to use approximate nearest neighbor, or ANN, which trades off a bit of accuracy for performance. But the accuracy that we lose is very, very little, and we get like 99% of accuracy, but we get a lot of savings in computational power. So this shows that when the number of elements, so with KNN we get linear growth with time, but with approximate nearest neighbor search we get ANN, we get logarithmic time if we use approximate nearest neighbor search. So one of the indexing strategies that we can use with Postgres and pgvector is this KNN. It's an open source project from Microsoft Research. It has very high throughput and low latency, and it beats other indexing strategies in terms of RAM and CPU usage. It's available on Microsoft Azure for Postgres, so we can use this indexing, this KNN index, to create the index on the vector embeddings that we have in the database. And then when we run vector search, the search will automatically use the available index in the database. So we will now see a demo of semantic search. So I have the database here. It's running on Microsoft Azure Postgres database. I will show the database, the table definition here. So I imported about 30,000 reviews from Yelp, and we can see here that we have a rating. They are the reviews. We have the review itself, and we also have the vector embeddings generated from this data. So. So this is the vector embeddings that I generated for the data using the Azure AI extension. So we will now run a couple of queries to see against this data to see how it works. So the query here, it's calculating cosine similarity between this search text. So I'm searching for reviews which match root employees. And you can see that I use the Azure OpenAI create embeddings, and this call will do a call to Azure OpenAI, generate the embeddings, and then compare it with all the embeddings that we have in the database table. And the results will be ordered by the similarity. So the less the distance, the more relevant the results will be. So if I run this query, we get the results. You can see that here we have different reviews. All of them are related to, so the query was root employees. So we can see here that some of the results mention root managers, root staff, the security guard, root desk bartender. So even though the query did not have these exact words, the results that we get are matching the query that I had, the text that I was searching for in the SQL query. Because the vector embeddings can capture the meaning from the text in this case, and when we do the similarity search, when we calculate the distance, we get lower distance. So the first column that you see is the distance between the query, what I was looking for, and the result, the distance between the search text and the summary text. So the first is the nearest, and the last is the farthest from this 10. We can also see another query here. So if I search for payment issues, for example, here we have another 10 results, and all these results mention some payment-related issues. They don't contain the exact words, but for example, here we have a Visa card we have the first result says instant payment. So all these results are semantically similar to the search phrase that I used in the query here. Okay, so this was the example of semantic search and how we can do it on the Postgres side without writing any code and doing everything on the database side. So we can generate vector embeddings directly from Azure Postgres and then use the pgvector extension to sort the results based on the distance between query and the data that we have in the database. So the next example is document summarization. So this is quite a simple operation. We take one document from the database and use the Azure AI services to summarize the document. So it will give us back the short summary from the text, and it can extract a couple of summaries and return the rank of the different sentences that it summarizes from the text. So if we look at this query, here we are calling the Azure Cognitive Service, and we are asking it to summarize the summaries that we have in the database. I will run the query now. So this is the summary that was passed to the query. And this is the result that was returned by the Azure AI service. So it extracted two sentences. Each of them has rank based on which one is more, which one scores how these sentences relate to the documents that we gave to the service. So we can see that this second one has higher rank score. It has score 1, so the score is between 0 and 1. So this second sentence has higher rank, and this is the summary that was extracted from the documents that we passed. So there are Azure AI service has two types of summarization. There is extractive summarization and abstractive. The demo that we saw was extractive. The difference between these two strategies is that extractive does not invent any new sentences or text. It will just extract the exact phrase from the documents that we give. It's faster and cheaper. With abstractive summarization, it will generate new summary from the text that we give. So it will be more. It will sound more like a human. So in the first case, we get exact sentences from the text, and in case of abstractive summarization, it generates new text. And we have different functions available in the Azure Cognitive schema. We can call summarize extractive like we did in the demo to get the extractive summary, and summarize abstractive for abstractive summary. So the next example that we will see is, so we saw semantic search to find results that match, to find the results that match this search. We saw how to summarize one document, and in this demo we will combine these two demos. So we will do a query that will search for relevant documents. Then we will summarize these relevant documents with extractive summarization. So we will get one key sentence from each search results. So we get we run a search, find 10 documents. We summarize these 10 documents and get 10 sentences with key sentences from these search results. And then we will use abstractive summarization to generate the summary which is global and common for these 10 documents. So this allows us to find the relevant documents and find what is the common summary of these 10 documents. So it runs in one query, but it kind of runs in different phases. So the part one is to find relevant documents, and then from these documents we get one key sentence, and then we summarize this sentence to get the global summary and find out what these 10 results have in common. So this is a bit long query, but we can go through this. So the first common table expression here, it does the semantic search the same way that we did in the first demo. It will generate vector embeddings by calling the Azure OpenAI create embeddings function. And it will find 10 documents in our database that match these search terms that I have. From these 10 documents, I generate an array of text so that I can pass this array in a single call to the summarized extractive instead of making 10 calls and passing each of them individually. It's faster to make one call and pass 10 documents and get 10 results back. So this is done in this part here. So we call summarize extractive again and tell the service that we want one key element, one key sentence extracted and sorted them by rank. So this will give us 10 records back and each of them will contain the summary of the text that we pass to the summarized extractive call. Once we get these 10 key sentences from the search results, we will concatenate those. Extractive summaries. And then we call the summarized abstractive endpoint to generate the abstractive summary, which will give us the overall summary of these 10 search results. And this way, we will be able to answer the question, what these 10 search results have in common. So let's run it. It takes a couple of seconds because it's, yeah. So if we look at the results, this is the abstractive summary that was generated from the 10 matching documents of the search that I did. And we can see that compared to the extractive summary from the previous demo, this one reads more like a human written text, as it's not just separate sentences extracted from the documents that we passed to the Azure Cognitive Services endpoint. So you can use this workflow to find what is the common thing between these 10 documents. So the steps are to find the relevant documents, do extractive summaries for each of them, and then do the abstractive summaries over those results. Okay, so the next demo is sentiment analysis. So the difference between this demo and previous demo is that the previous demos were all generative use cases. So in case of summarization, the LLMs generated some new text from the documents that was passed to the service. But sentiment analysis is a classification problem. So it will give us, as a result, whether the document is positive, neutral, negative, or mixed. And it will also give us confidence scores for the results. So it's a deterministic task, but we can still use AI to examine the data and find out the sentiment. And the final part is PII detection. So PII detection allows us to find personal information and other sensitive information in the data we have. It can find and also redact the personal information from the text, so we will get back the result without any personal information. It's not so similar to the sentiment analysis. It's not a generative task. It's very deterministic because it will simply remove the personal information, and it will also give us all the personal information that it detected separately, so we can process them if we need to. So let's see the demos of these two examples. So in case of sentiment analysis, we call the Azure Cognitive Analyze Sentiment function. And here we can see that we have the ratings. So 4 is the highest, and 0 is the lowest. And if we let's remove this summary column for now. If we look at the result, we can see that we get positive for the first one, we get mixed and neutral for the next two, and negative for the last one. And the numbers indicate the confidence score of positive, negative, and positive, neutral, and negative. So the first one is definitely positive. The second one, which is mixed, has 0.6 confidence score of being positive, and so on. The third one is neutral with its own scores, and the last one is negative, and the confidence score of it being negative is 0.88. And the final demo is recognizing the PII data inside this text. So we are now calling Azure Cognitive recognize PII entities for this single document. So it's quite a long text, so I have copied it here. So here we can see that the first part is the text that was passed to the recognized PII entities. We can see that it starts with Mr. Something, so it's last name, and then we have also the address somewhere here. So, and the second part here with redacted text, this is the text that we get back from the cognitive services. It has identified all the PII information and replaced it with asterisk. So all the PII information is redacted. So if we want to show it somewhere, but we want to hide personal information, we can use Azure Cognitive Services to redact all the PII information. And the call also returns so the second part of the result is all the PII entities that the Azure Cognitive Services recognized in the original text. So this is also returned as part of the API call. So we can also process them if we want. So all of them, it has the type, what type of PII information it is. For example, the second one is address with the confidence score of 0.93. The third one is date, and so on. So these are all the PII entities that appeared in the original text. And this text is the text that was passed with, but the PII information here is redacted for safety. So that was all today. So you can find more information on this link on the Azure Postgres documentation. Azure Cognitive Services has many more functions that you can find there. And if you have any questions, I can answer them.